Hello, everyone. Welcome to Exploring Artificial Intelligence with the City Data Science Society. We're joined by Marios today. I'll let him introduce himself in a second, but he's a PhD student from Heriot Watt University in Edinburgh. He's going to talk today about the ethics and research he's doing into AI and a little bit maybe on his work at Amazon as well. So thank you, Marios, joining us.
Yeah.
Get started.
So first of all, I need to say that out loud in the public. I'm giving this talk as part of my own interest and not Amazon's. I have to say that for legal reasons. I won't be able to talk exactly about my work at Amazon, but I will mainly talk for my research during my PhD. I can give you a few ideas of what I'm doing. I'm working on the Alexa research team, structured knowledge team. We're basically trying to make Alexa more knowledgeable, and we want to do that by leveraging structured data like web tables from the internet, Wikipedia, and so on and so on. So what my main research at Amazon is to be able to interpret this structured knowledge. And for example, if someone asks Alexa, who was the tallest president of the United States, to have higher chances of answering this question, because obviously Alexa in the backend has more than one modules that actually tries to give an answer. So I'm working on one of these modules. So that's all I can say. And for my PhD at Edinburgh, I'm also working on conversational agents and grounding language to images, maps, like Google Maps or OpenStreetMaps or navigational charts. I'm going to talk about it later. So when I say grounding, I mean when you say, for example, a word like cat in your mind, a picture of a cat appears. So your mind automatically grounds the language to the 3D world representation or the internal representation of your brain. So I'm doing that, but for maps and natural language, in order to help marine operators to control autonomous underwater vehicles. So to get started, this is gonna be a long talk, I assume, and we might get a bit tired with all the knowledge. So please, if you have any question at any time, stop me. This is not a presentation where I just talk and by myself, especially in this environment online. I can't see your faces, so I will cringe a bit if I start making jokes and I don't get any response. So please feel free to stop me at any moment. I will, after almost every slide, I will try to remember to ask you if you have any questions or if I'm going too fast or too slow. I will start with a general overview of artificial intelligence, what is learning and all that, a brief history, and then I will go into deeper explanation of machine learning, deep learning, a bit about my research, and I will hopefully, if time allows, I will end with some ethics. If I see that the time is not enough, I will skip my research and go directly to ethics, because I think is one of the most important things. Also, I don't know if you noticed, but the tables goes 1, 2, 4, 5, 6. I missed the 3. I don't know how to count, apparently. So let's get started. What is AI? Well, to understand AI, artificial intelligence, which for some can say it's just fake intelligence or coping intelligence. Well, to answer this question, we need to first understand what intelligence is. And intelligence, if you look at the dictionary or for many research online, can be the ability to accomplish complex tasks. And a complex task can be even writing with your hand, like the precision needed to actually move all your motor muscles and nerves and to synchronize them with your eyes, your perception, and make decisions of what gesture to do next to write what you think. This is a complex task. A simple task could be, for example, a game like tic-tac-toe. So is there more than one intelligence? Is there if we wanted to categorize intelligence, how would you do it? Some people say, okay, there is emotional intelligence or logic and all that. In the AI, I would like to split them into two categories: narrow and general. And I I think the first time was in 2014 when DeepMind CEO Demis Hassabis introduced this concept: artificial general intelligence, an intelligence that can tackle any task without any structured rule-based knowledge given to it. So narrow intelligence, to explain, um, narrow intelligence is intelligence that's specifically built to tackle one problem. We built a chess engine like Deep Blue that beat Kasparov in 19, I don't remember the date, for example, was a narrow intelligence like artificial intelligence like that. The purpose of this machine was given all these strategies by humans, all these rules, if else, if else, if else, and so on, and trees and tree search and all that, to pick up the best solution, the best possible outcome, and do perform an action, but in a closed system, a specific task. It would never be able to adapt to another game, for example, or in speech or in vision or in general other modalities. General intelligence, on the other hand, is flexible, and that is because it has the capability of learning. It has the capability of generalizing and adapting to new scenarios. So, if we take this meaning of the general intelligence, we could essentially, if we built it, we could make it play any game, for example, without specifying any rules or anything. And that's what it means when we say no special casing or pre-programming. We're not saying any rules. For example, if we wanted our AGI bot to learn to play chess, we wouldn't give it any strategies or any rules or anything or any programming. We'll just give it the environment, of course, give it the actions that it can take at each stage, and then it will learn by itself how to play. This is artificial general intelligence. So before go any further, how can we make an artificial general intelligence? How can we make a machine learn? And what is learning exactly? For us humans, learning occurs when we gain a mental or physical grasp of the subject. For example, when we were born, we didn't know that this was a book. We started touching things, exploring the world, and slowly we started building a mental model of the objects around, faces, recognizing face, and all that. Our subconscious is one of the most efficient machines to learn by that, and that's why it's also one of the easiest mechanism to hack. Our subconscious can easily be biased from the outside world, and that's why, for example, there's been all over these years the brainwashing that's happening because of the media, and people are raging on that. And that's because our brains, if we don't consciously control the input, it will be so fast to learn and adapt, and this can cause problems. So when we learn something, when we actually grasp the context of something, we're able to interpret it in our own words and combine it with knowledge that is already in our brain. That's the amazing thing about our brains, and that's what we want an artificial general intelligence to be able to do, to combine prior knowledge with new knowledge, generalize and adapt in new situations. I want to ask any questions so far. I don't know if I'm going so fast or if you're understanding.
It sounds good so far.
Yeah, Nikos, you? What about you? Are you
No,
there?
everything is fine. Everything is fine,
Okay.
Marius. Thanks.
Okay, cool. So I will give you a brief overview of a basic. So I don't know how many of you. Well, I wish I could get a response now, but I don't know if you're aware of neural networks. I'm going to explain later a bit more about them. But one of the ways to teach a model, an AI to learn, is to have what is called neural networks. And artificial neural networks are basically inspired by our own neural networks. And the reason why it's such a revolutionizing technique is because it has the ability to adapt to new data. It has the ability to change and keep these change in a sort of memory. And how are we doing that? Like, how do we make numbers learn, right? Like, everything is just numbers. So in this, there are a couple of steps. First of all, we have, for example, if we wanted to teach a model to recognize cats and dogs, we have a picture. For us, a picture is just light that comes through our eyes, and our brain does some pre-processing, and we understood that this is a cat because it maps well with our mental model of a cat. So in a neural network, this image is just a vector of numbers. And this vector of numbers are going to be multiplied by other numbers. These other numbers are just neurons. We call them neurons, okay? We multiply them all together, and then we pass them through layers. If there is more than one layer, we call them deep learning, deep neural networks. And what comes out of it? Well, in our case, humans, speech might come out, or actions, or I don't know. We need to have some things that can go out of it. In a classification task where we want to say if a picture is a dog, a cat, or something else, we want the model to output the category of this image. So basically a number. And with these numbers, we tell the model what these numbers are. If it's a 0, means, for example, it's a cat. If it's 1, it's a dog. If it's 2, it's a frog. Depends how many classes we have, okay? So that's what's happening. So in the forward pass, we pass these numbers of the cat, and then in the beginning, the model just randomly, depending on the multiplications that happened, gives us one of these numbers. So it might say dog or a cat. We take that outcome, okay, and then we have this loss function that basically compares that outcome with a gold label that we already have. This gold label is taken by annotated datasets, and this is happening in supervised learning that I'm going to talk in a few slides as well. So in the supervised learning, when we have a dataset, we have thousands of images. For each image, we have a label: cat, dog, for example. Let's say that we have a binary classification task, in this case, binary. So 2 predictions, either a cat or a dog. If the model predicted wrong that it's a dog, and the loss function is going to give us a high error. And then this number, this error, we just calculate the derivative in order to change the numbers that are going to multiply the image. Okay, so we go backwards. That's called backpropagation. And then we need, the final step is an optimizer, which is going to say how much are we going to change the numbers of our network. So if we made a mistake, what is our learning rate? Should we multiply with 0.1, for example, or our neurons with 0.2? How fast do we want the model to learn? And then we need to think of other things such as overfitting. If our learning rate is high, we might overfit, and so on. So I gave you a brief introduction to this methodology of learning for neural networks, but it's okay. If you're familiar with, I'm sure you got it. If you're not, it's fine. We're gonna move on, and the more I explain, I'm gonna go back to it in a few slides. So I want to say also I want us to time travel a bit in a few years back, before the modern computers, before all this craziness. So basically, Alan, I don't know how many of you know Alan Turing, but basically he some people consider him to be the father of artificial intelligence. He was one of the greatest mathematicians of all time, and he also played a major role in solving the enigma problem. So Alan Turing was saying what we want is a machine that can learn from experience, and that's what is true intelligence. True artificial intelligence is not about 100 programmers sitting down and writing 1,000, a million, or a million rules. True artificial intelligence is one that you can just give it the world, give it the data, and then the model learns by itself. That's what we want to achieve. And from his name, we got the Turing test, which is basically the artificial intelligence test, where if an AI passes it, it means that it's smart enough to confuse us of not knowing if it's an AI or a human. And usually in the natural language processing community, we want that's our major goal. We want to build a chatbot that you can converse, you can talk with it, and you don't even know if you're talking to a machine or a human, because it's that smart. It can convince you that you're talking to another person. And there are many online chatbots like that. Most of them are not that good, but we still haven't solved it. So yeah, unfortunately, Alan Turing was convicted for gross indecency for his relationship with a man, and that's another issue. We're gonna talk about the ethics afterwards. That there are also other things that unfortunately politics and money do not allow us to do, or or scientists are generally being judged all the time. And we're going to talk about that because it's a very important theme to talk about, especially on the level of artificial intelligence. So I will start now going a bit more from all the general AI. I'm going to go into more specific topics. Before I go into, do you have any questions so far? I've been very general, talking about general topics. So I don't think, unless if you can hear me, I think you should be following, right? Any
I think we
questions?
are good, Marius. I think we are good.
Yeah. Okay. So artificial intelligence originated in 1950s. Alan Turing was one of the most important figures of it. Data science is also a subset of artificial intelligence. And then after moving on from rules to more sophisticated algorithms, machine learning came about. And what is machine learning? It is the practice of getting machines to make decisions without being programmed. And it has been around since 1960s. The reason why we've seen all this excitement about machine learning and deep learning, which is the child of machine learning, recently is because of the hardware power that allowed us to actually train models, so sophisticated models. Until the 2000s, we didn't have the capability, for example, to have enough complex neural networks to actually make a very smart decision, such as classifying pictures from 1,000 different classes from ImageNet. ImageNet is one of the main tests for computer vision tasks, and it has basically 1,000 different classes of animals, and is basically all solved at the moment. We can predict all these animals with an accuracy above 90%. And convolutional neural networks, which I'm going to talk about them in a bit, played a major role at solving that. But all these, in theory, they're not new. They come from 1970s and 60s. I don't know if you can see very well, but this is a nice graph that basically explains what is happening through the years. So let's look at it a bit together. So we start with natural language processing. We started some rule-based systems to do some spell and grammar check, and we moved into the supervised learning, where we get a recording, and then we have annotated labels, a data set that has text of this, and then we teach a model to build patterns and try to translate this voice numbers to text numbers. Then we move on to personal assistance, and in the future we want to have real-time dialogue and translation, and by that we mean really AI that you're gonna be able to cooperate with and solve tasks together. We're not at that stage yet. We have a single turn conversational agents such as Alexa and Siri, where you can say, "Oh, Alexa, open the YouTube and play Pink Floyd," for example. This is solved, and speech recognition and computer vision are considered solved tasks at the moment, even though depends on your in the speech recognition problem, for example, depending on where you are on earth, which city, your dialect and all that, it still might not be perfect, but it is considered a solved task. And um, yeah, computer vision, we are moving towards self-driving cars and more specialized autonomous agents that are gonna need vision as well. Pattern recognition, in general, the things that I mentioned, reasoning and optimization is mostly on recommendation systems, robots, and problem solving. So for example, in science, we want to be able to have an AI that can read, for example, all the scientific papers about a topic and being able to come up to solutions or invent something new. These are new areas and topics of interest. I'm gonna send you all the slides so you can look at it, but this is an old graph from 2016, so it might be a bit outdated. Any questions so far? Nick?
No, we don't have any questions, Marius. Thanks.
Okay.
So guys, as a reminder, you can type questions in the chat and we'll be able to ask Marius. So if you want any more information on anything, you can just stop us in as we go through. Cool.
A nice graph, yeah. Okay, so a nice graph that I want to show you is Hans Moravec's, and it's the landscape of human competence. And just to show you a bit of where we are at the moment on the state of the art, where this on the sea level, it's where the AI is solved at the moment. So arithmetic, chess, the game of Go, all these are solved tasks. But translation, driving, speech recognition is almost solved. So it's close to the sea level, but there are exemptions. So as I told you, with the dialect issues, or in translation, some people say that it's already solved, but again, depends on the context. If we have like a big text in Russian and the context is completely different from what the neural network is trained on, it will not be able to predict exactly correctly as correctly as a human. So some people say it's solved, some people no. But for example, we're still way behind on book writing, art, cinematography, science, theorem proving, and these are tasks that are gonna worry us the next 50, 100 years. And I think the AI research is moving towards that. Self-driving cars, I think, is gonna be a solved problem the next 10 years as well. So I will now, as I told you before, I will explain some types of machine learning.
Marius, before you continue, sorry. First, we have a question. What would be another unsolved problem besides self-driving cars? If you can talk about a little bit. And also, we have created a pool that Ben will upload, will show it to you like in a bit after you answer the question. Do you want me to repeat it or?
Yeah, repeat the question.
So, what would be another unsolved problems besides self-driving cars?
An unsolved problem. So meta learning is not, which I'm going to talk later. Meta learning, so learning to learn, is an unsolved problem. What else? I have some other later on slides that I'm gonna talk about unsolved tasks and future research. But yeah, it's still a bit early because I need to explain some concepts first. But yeah, I will talk about that when we go to the applications stage. Good question.
Okay, thanks.
Okay.
Ben? Yeah.
Yeah, so we
Yeah.
just made a quick poll just to test, just to see if you guys are paying attention. So just 3 questions. I'm going to launch now. This should come up on the screen. This should be relatively simple. And let's see.
And
Okay.
just on the yeah, okay,
Yeah,
yeah,
go on.
yeah, on the context of the things I was talking about the conversational agents. So the a fully dialogue system with turn taking that is also goal based is still not solved. So um, you wouldn't be able to have a proper conversation with an agent that has a personality, let's say, or a proper conversation, or an agent that can keep history in its mind. So there are at the moment conversational agents that you can ask a question, you get an answer, and then you ask another question, you get another answer. But if, for example, you say, "Oh, on the first question I asked you, did you mean that?" The bots are still getting confused. They can't really associate past knowledge that well, even though with the new transformers and attention models we've seen a lot of improvement there. So for example, an attention model was trained on the Harry Potter books, and it wrote a full chapter of new Harry Potter, and it was actually keeping track of the characters. So it was saying Voldemort just appeared in the middle of nowhere, and Harry Potter tried to kill him. And in the next sentence, he's like, Voldemort didn't like it, but Harry Potter was so satisfied with his powers. So the model was actually not just reintroducing random characters. It had the flow. So it introduced Voldemort. It's gonna talk again about Voldemort. So that is we are on a good progress on that, but it's still just pattern matching. It has no idea what it's talking about, or it doesn't have any sort of consciousness or all that. Like we're gonna talk a bit more on that later. So yeah, is the poll done or
Interesting. Yeah. Entered polling now. Can you see the results, Marius?
no? No.
Okay, that's fine. I'll share the results here. So the first one was just what is AGI, and it's AI that can solve many tasks rather than specific tasks. What is the Turing test? And it's a test to see if a computer is indistinguishable from a human. I think some of the answers weren't done properly in this poll, but we know which one's correct. And when did deep learning originate? It was the 1970s. So yeah, most of these are correct. They're increasing in difficulties we went down. So yeah, that was good. Cool. Thanks.
Okay. Yeah, that's good. Thanks, guys, for paying attention. And remember, this is not just a presentation that I'm only talking. We're having a discussion here. So the slides are just there to give us a context to talk about. So stop me at any moment. Okay. So let's move on to types of machine learning because I still have a lot of things to talk about. So machine learning, it's split into 3 main types: supervised learning, unsupervised, and reinforcement learning. These are the classical types. And then from them, self-supervised, meta learning, evolutionary algorithms, and many other AI concepts appear that we don't have time really to go into all of them. So to give you a brief explanation of each of them, I will go back to this slide if you want to have a look. But for now, supervised learning, as I said, is when we have labels, when we have some data, images, audio, text, and we want to make a prediction on these samples in these examples, and we have that label from humans. Humans actually called annotators. They sit down and said, this picture is a picture of a cat. This picture is a picture of a dog. And the only thing we do is we give all these thousands of data to a model, a neural network model or any other statistical model, and we get a prediction. If it's a wrong prediction, we tell that to the model. Somehow there are many optimization techniques that we're not going to go into a deep detail, that changes the weights and the numbers of the neurons in order for next time when we pass that image, the model gives the correct answer. Unsupervised learning, on the other hand, is when we do not have any labels. We do not have any annotation. We have 1,000, a million images or videos. For example, on YouTube, we have uh, many hours. Like I think every minute 300 hours of video is uploaded on YouTube, if I remember correctly when I was checking it. So these are supervised data. We do not have annotated labels, and the techniques and the way we teach a model something with this data is by giving the model all the data, and then the model tries to find patterns and cluster them into different categories. So imagine we have a million images. These a million images are either of dogs or cats. Okay, we don't know which are which, but we know that they're only dogs and cats. Okay, so we can tell the model, oh, there are two types. Okay, I want you to separate them and learn the characteristics of this, the features of this data. So the model is rearranging weights, and again in a similar process with a comparison, this time of the data themselves. So they end up with two categories. If we don't give it a number of categories, it will try, depending on the search hyperparameters we give it, to see if there is a third category or a fourth and fifth. So the reason why this type of machine learning is very powerful is because in this type of data, we do not have the bottleneck of us humans having to go manually and put labels on them. We can literally just crawl around the web and gather millions of text, millions of audio, and millions of images and video. And that's, I think, where the future of AI is going. And in this category is what is called, according to Jan LeCun, self-supervised learning. It's where a model given millions of data that we do not know what these data are, is trying to learn to represent them, a better representation. And then if a model knows, for example, we have given it millions of images of books, okay? And it knows how a book is. It has usually some lines here, usually is a square or it can be a circle. It learns this by all the thousand images of books it has seen. And at one point we go and say, oh, this is a book. So that's how we go from unsupervised to low supervised learning, where the model already has a very good representation of the world, and then just by pointing at only one sample, the model can understand, oh, so all the things maybe that look like that are books. And that's how babies actually learn. In the first few years of our life, we just do random shit, like we don't know, we touch, we we say random sounds, we listen to things. But this is the unsupervised learning process that needs to happen in order for our brain to build the most efficient representation of the world. And that's why when we're young, we can adapt faster and learn easier, because we still haven't built very strong connections of representations of the world. We can still change them, this representation, over time. But if all my life I have been seeing this color and I have been calling it orange, suddenly it's going to be hard, maybe, for me to call it green. But not that hard. Like if I say it every day, I think after a few tries of minutes, hours or days, I will be able to override my subconscious knowledge of the color orange, and it's going to be green. And these are all very fascinating techniques, and that's where supervised learning comes in. So to get back to this, reinforcement learning is also a very interesting strategy that has become very successful after 2014, especially in games. And it's basically the way to teach something giving rewards, like the same way with you train a dog, for example. It does something. If it's a good thing, you give it a reward, some food or something. If it's bad, you don't feed it, and that's how you're training. So you reinforce good actions, like actions that you want the model to keep. And in games, it's so easy to do that because we have either you win the game or you lose. So imagine if you put a neural network to play 1 million games, and at the end if it lost or won. Depending on the outcome, you can enforce the connections of the neurons, so the model can learn actually by itself. So reinforcement learning, we don't really need data, but we need a sort of simulator. We need an environment that our model can try things. So it's basically trial and error plus a rewarding mechanism. And in closed system as games, this task is currently solved. Like DeepMind, which I'm gonna again go into detail later, which invented deep reinforcement learning, which basically is reinforcement learning but with many deep layers of neural networks. That's it. That's all. It's no different concept. It's just reinforcement learning with neural networks, deep. And yes, what they have managed to do is build AlphaZero, and AlphaZero is only one program that can basically play any game in the world at the moment. Any game that has, as long as it has a closed loop, okay, it can play football or rugby in the in the streets, of course. But if it was on a simulated environment, like in FIFA, and you let it play with itself for a million times, which in human lives can be 100 years, it will actually, you will never be able to defeat it. It's impossible. And actually, we are at a point where actually this algorithm is suggesting strategies in games such as chess or Go. I think, I'm not sure about this, but I think there are books of new strategies that the algorithms came up with, and this is actually amazing. But we should remember that this is not magic. It's just pattern matching. Still pattern matching that is programmed using a rewarding system of, in this case, of winning the game. So it's nothing more than that. It's not truly intelligent, but it can truly learn. So these techniques will never be able to invent chess. They will never be able to invent a new game, but they can become better than humans in every game. Okay, just to say that so you all know. Any questions on these types so far? All good, Benjamin, Nikos?
No, we don't have any question, Marius. Thanks.
Okay. And this diagram is only here to show you that evolutionary algorithms are also part of AI, and usually they go under unsupervised learning as well, because we don't need labels. You just need an environment, a simulated environment, like in reinforcement learning. But this time, instead of having a rewarding system, you use sort of Darwin's theory of evolution, basically. So you create an initial population of 200 algorithms, bots, or AIs. You put them in an environment, and you let the environment happen, like the game to play, for example, or whatever you're doing. And the survivor or the winner, which might be one or many, is kept. The others are discarded, and the new neural network or the new AI is inheriting characteristics, numbers, or neurons, or whatever is your representation, from the winners. And you do that for many generations, and you end up with some sort of smart behavior by accident. That's called evolutionary algorithms. Okay, so let's go into even deeper. Meta learning. So what is meta learning? Meta learning is the idea of learning to learn. So before I talk to you how a neural network learns, we have an image, we pass it through some numbers, we get an output. Okay. But the architecture of these numbers is already predefined. We humans chose this behavior because we are artists, because we have our experience from the past, and we know that if we put these numbers in this specific structure, we're gonna have higher chances of in inventing something intelligent. Meta learning, though, is a technique that allows the computer pick up these hyperparameters. For example, the topology of the neural network. Are we going to use a CNN or a convolutional network, or how are we going to multiply the numbers with themselves, or what learning rate, or all these hyperparameters that we humans choose? Meta learning can learn to choose it for us. Um, one way that it does it, it can be through evolutionary algorithms. That's why I mentioned you. Evolutionary algorithms is one of the strong topics in meta learning at the moment, or double derivatives, which I'm not also going to go into detail. But all you need to remember is that meta learning is basically like in evolutionary algorithms. You have many structures of the network, and then it's like many children. Each child plays or predicts something, and then the big parent model was like, okay, this child was good, these parameters are good, this structure is good, so I'm going to keep it. And usually it can be trained with evolutionary algorithms or with gradient descent as well, or derivatives as the standard neural network.
So, Marius, we have two
Yeah.
questions. The first is, which type of machine learning requires the most processing power?
Mm-hmm.
And the second one, yeah, go on.
Yeah, so, well, neural networks require the most processing power, usually deep neural networks, because you basically do, the deeper the model, the more processing power you would need in order to perform all these multiplications. Because basically all the neural networks are basically vectors and matrices of numbers that multiply with each other, and they change the outcome. You get an outcome. So the deeper the network, the most complicated. And the state-of-the-art convolutional neural networks or transformers or attention modules, they use millions of parameters like that. Our brain uses like petabyte of data probably, but right now on the models are on the gigabyte scale. And in these deep learning models, that's why we use the GPUs, because GPUs uh, are very specialized machines, modules that are able to do these multiplications much more efficient than the CPU, because GPUs were built basically to do uh, multiplications and to display numbers for games and graphics, which require a lot of computation. And that's why neural networks are trained on GPUs. It might, the same time that something will take on a GPU 15 minutes can take 2 days on the CPU. So yes, deep learning techniques are definitely the most power inefficient, not inefficient, but they need the most power than all the other machine learning techniques, I believe. Yes, but also always it depends how much you scale it, and usually all the techniques are being combined nowadays. I think in every AI subtype there is a neural network nowadays. Even if evolutionary, I used to play with some evolutionary techniques, and I was basically evolving neural networks. So I didn't run it on a GPU. So for example, it took 10 days. I'm going to show you later a reinforcement learning example that I did on my project for my undergraduate in Manchester. And it took 10 days to do something that on a GPU with a much deeper model would take a few hours. Yeah,
Okay.
what's the next question?
Okay, then the next is, which tools and software do you use in your work, or which one you can recommend for people who want to explore more about AI?
Uh,
Probably frameworks, or I think, uh, yeah.
well, I would definitely, first of all, as a programming language for easy prototyping, I would recommend Python. I'm using Python, and for deep learning, one of the best, there are two basically strong and very good libraries that almost everyone uses. Is the first one is TensorFlow, and the other one is PyTorch. They are both amazing because they have you can like do whatever basically you want, and you have a lot of already models behind predefined for you that you can use as well, but it might be hard to learn for a beginner. So if you're a beginner, you just want to see something run, you can use libraries such as Keras, Detectron for object detection. What else? I think these two are high level enough, but if you really want to experiment, it might be hard in the beginning, but I think you should definitely go with TensorFlow or PyTorch. TensorFlow is built by Google, PyTorch by Facebook. I use for my experiments usually PyTorch, and I know PyTorch, but they both have their pros and cons, which you can choose depending on you. I would definitely recommend PyTorch because of the dynamic nature of the graph, but TensorFlow is amazing as well. Any
Okay.
other questions?
Okay, thanks. Yeah, no. Sorry. Yeah, one more. Probably he refers to frameworks. Could you replace their names?
Yes, Keras. What else did I
TensorFlow.
say? Tens- PyTorch,
Uh,
TensorFlow, Keras, PyTorch Lightning. There are there are many, but if you really want to prototype fast and also build a strong understanding, I would recommend PyTorch or TensorFlow because you can actually see all what happening behind it. Keras is a very high level. You just call with a function, you're gonna call a very powerful model, and you have no idea what is happening in the background. With PyTorch and TensorFlow, you can see. And the good thing about these two frameworks is that the documentation online is amazing. It's very clear, and you can follow it. And there are many easy examples. You can go right now. I can show you. I'll show you afterwards. You can go right now and experiment with this with some easy examples and have a model run on your CPU or GPU in seconds. And Detectron 2 for object detection. So if you want to build a model, it's also high level like Keras. It's built on top of PyTorch, again from Facebook. And Detectron, for example, even online you can experiment. If you don't have a GPU, you can still use it on Colab or Jupyter. You can write this down, Nick. Uh, so to do object
yeah,
detection,
don't worry. I got it.
and it has the state of the art models that performing the best right now already there for you. And the tutorials are amazing. I think I have some slides. Maybe I'm gonna talk a bit more on them. So yeah, Detectron 2. Let me know when you're done, Nick.
You can go on, and I will post in the meantime.
Okay. So remember I talked to you about self-supervised learning, which is sort of part of unsupervised learning. So the idea of self-supervised learning is that this time we do not try to just cluster together examples with similar features. What we want to do is leverage all this data in order to learn a strong representation of the world. So, and for example, in any sort of data, images, text, audio, the way you do self-supervised learning is you take as an input your sample, so the image, you mask meaning you remove some of the pixels that you want your model to predict, and then the model is trying to reconstruct the image. So it's like saying, imagine you have 1 million pictures of a book, okay, and you always hide, like for example the angles, okay, and you want the model to predict the pixels of the angles. So the idea is, if you do that for thousands and millions of examples, the model will sort of understand what a book is supposed to be. And it's a very powerful idea because you can do it in unlabeled data. That's why I think if we ever solve artificial general intelligence, the main components is going to be self-supervised learning, because that's the learning we humans do when we are born. We try to predict. Our brain is always trying to predict. So as you can see from the picture, predict the future from the past in a video, predict the future from the recent past, or there are different. It's up to you how you're going to train the model. And for example, in an image, if you hide some objects, that's when it's predicted occluded from the visible. So you have, let's say, a picture of a room with balls, okay, and you hide some of the balls. The model will will understand, because the picture is full of balloons or balls, it will mostly uh, learn that in this missing picture probably there are more balloons or balls. This might not always be right, of course, but the idea is that if we're able to predict the unknown, it means we know it very well, we understand it. If I hide one of my eyes, you all know that I have an eye here, but it might be possible that I'm blind or I have lost my eye or something. So but the main idea is to understand the representation. Yeah, meta learning. We talked about meta learning. Reinforcement learning. Okay, and also there is a Q learning demo that I will show you. So reinforcement learning, as I told you, is the type of machine learning that we use rewards to train a system. So no labels. So imagine we have one box. This is our agent. Can you see my mouse? Nick, can you see my mouse?
Yes, we can.
Yes,
Yeah.
okay.
Okay.
Yeah.
So forget about the what it's inside the box. We have a box, it's our agent. We have a box, is our world. The only thing we get from our world is some rewards, good, bad, good, bad, good, bad, and we observe the state. So it can be an image of the world, can be an audio, it can be text, and the output from our agent is an action. So if you were playing the game of chess, you want to know what's the next move is going to be in the world, and this is going to be the chess. The observed state is a list of all the characters on the chessboard or an image of the chessboard, and the reward, um, we can have long-term rewards, so the end of the game we won, or if you are going to eat a pawn, like that's a short-term goal. And how you represent the knowledge of the agent can be either with a deep neural network, and is going to be, or like a box with where you match the states with action. So if we have a knight and a king here, when you take this action, but we do not sit down and program these states. We it's in the beginning, the state action prediction is empty, and the model, while building the policy or the values that it gets from the rewards, it's trying to pick up the best action given a state. That's all reinforcement learning is. So given a state and the reward given action, something like that. And okay, let's see. So in this demo, we have a 2D agent with 9 eyes pointing in different angles. So the agent does not see the whole game that I'm going to show you. It sees 9 points. And every of these 9 points has a distance that can see if there is a wall in front of it, if it's a green ball, or if it's a red ball, that a red ball is bad, green is good. So the agent, and what can the agent can do in this environment is, using one of 5 actions, it can turn in different angles. Okay, so let's see if this is gonna work. It's a I think you're gonna start understanding a bit. So this is our environment. Our environment has walls, has red balls and green balls. These lines are the 9 eyes of our agent, and the agents, every second, it randomly presses the buttons, go turn left, right, go up, down, 5 actions. And the more green balls it gathers, the higher the reward we give it. And so you see the age is already 4,000 moves, and it keeps growing, and we try to minimize the loss. These, you don't need to understand exactly what these are, but it's basically the metrics we use to measure the intelligence of the. So if we go faster, 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 you see slowly it's starting to hit less in walls. And I think by the end of the training, if you train it for enough, it becomes very old. It will not hit at all in walls, and it will only pick the green balls. So you can play around with it, but that's the main idea. The only thing, so the input to the agent is just values from these 9 points, okay? And then when you pass them through multiplications, this is just layers of a neural network. And at the end, you get 5 functions. Go up, left, right. And here you see some results. I think every time it hits, it dies, or no, I'm not sure. Go very fast. So see, now it's lagging a bit. I don't know if it's running on a GPU online. It runs on the Stanford servers. Okay, go fast. It's still not very smart, but if we sit here for some minutes or even hours, we're gonna see that it's gonna get smarter and smarter. And obviously, this is just a dumb example. It says takes 10 minutes to train with current settings. If you're impatient, scroll down, load an example per training network. Okay, we're not gonna do that now, but yeah, basically, when you load a pre-trained network, it means these values here that we have, these numbers that multiply our input, we save them in a file and we just load it, and then our model is already very smart because we trained it in the past. Okay. Well, I have many of these demos that I want to show you, so hopefully we're gonna have time. Okay, so some information overload. Please follow my mouse because you're gonna get lost. I just want to show you some architectures. So the most basic deep network is this one, deep feed forward. We have some input, and then we do multiplications with these green balls, these neurons, and then we get some output. This is the basic deep feed forward network. All layers are connected with each other. Recurrent or long short-term memory LSTMs have an extra power. It is the power of time, and by time I mean we have information from the previous step. So in each stage, we have an input, and this input is passed through some hidden layers. These blue layers here can be many green, but they don't show it here. And then in the next second, every second we gather data. So LSTMs usually are good for time samples like videos, audio. In the speech recognition, the state-of-the-art models use LSTMs or transformer networks, which I'm going to explain in a bit what they are. So at every point in time, you have an input from the environment and also information from the previous time, from the previous state. In a feed forward, you only have one dimension of time. So you just give it an image and get an output. Done. In the long short-term memory, you get many images. And each time you get an image, you also have information of your previous state. Gate recurrent units is also part of recurrent neural networks. Deep convolutional neural networks are like feed forward, but this time we perform specialized computer vision pooling or different kind of multiplication, more sophisticated. And these models are harder to train on CPU because the CPU is even slower. So that's why when you train a big CNN, you always need a GPU, or it's going to be much faster. What else do I want to show you? Variational autoencoders and autoencoders is basically you have an input representation. We map it to an internal representation, an internal vector. So you get your inputs and you come up with your own vector of input. So right now, imagine I look at this book, okay? This book has these pixels. My brain, though, inside does not keep all these pixels. It has its own representation of the book. And given this internal representation, I can use a decoder, my hands decode, to do something. I can touch the book, okay? And these networks are used when we want to create a latent space, a better internal representation. And given this internal representation, we can do many things. We can predict, classify, or perform actions or whatever. What else do I want to show you? Deep residual network is exactly like deep feed forward, but we have connections between layers that are not next to each other. So from the first one, we can go immediately to the third one or the fourth one. And this allows, because when you train a neural network, when you do back propagation, when you multiply, when you do your derivatives at the end to change the weights, okay, this number, if you are very deep, it's uh, it might get affected in a bad way. That's where we have the gradient loss, or where we might not be able to train that well the model. And what we do, an easy solution, is to build connections between these networks. And all we mean by this building connection is this: instead of this neuron only being multiplied by this neuron, we also multiply it with the other one. That's all we mean by a connection. A connection is basically a multiplication and a sum, depending again what you're doing. But we're talking very high level now, so we're not going to go into it. And the other ones I really want to talk about is the GANs, generative adversarial networks. So yeah, the other here, you can have a look, you can Google all of them and see what they are, but we do not have time to explain right now all of them. So generative adversarial networks came out in 2015, is one of the best inventions of the 21st century on AI. So what they are, GANs is a model that can create from nothing data, basically. So that's why many scientists use them for data augmentation. For example, what's happening? We have a random noise, so this is nothing. We pass it through a generator, we call them, so which is a deep feed-forward neural network, or in this case, a convolutional neural network, because we want to build an image, and we generate a face. In the beginning, this face is going to look like that. It's going to look like, or even worse like that. It's not going to look at anything, okay? So you're going to ask, how can we know how can we create data from nothing, right? So what we do is we get some data of real faces, okay? And we get these very bad generated faces. And what we do with these two outcomes, the fake and the real, we pass them through another neural network called discriminator. And the only job of this discriminator is to understand if it's a fake or a real. So if it's a fake, it gives this information back to our generator and says, man, this looks complete shit. It's not it's not at all close to the real how a face actually looks like. So you need to change it. Look how a real face looks like. And generator is like, oh, okay, I'm gonna change my weights a bit and try to generate. And the job of the discriminator is also to get smarter at predicting if it's a fake or real. So in the beginning, both of them are quite bad. So you might ask, how then, if both are bad, how are they learning? So it's sort of like the dilemma: did the chicken first make the egg or the egg make the chicken? Is also, so that's why they call generative adversarial network. It's like one, it's attacking the one is trying to deceive the other, and like in evolution, they get smarter and smarter. And this discriminator becomes very good at distinguishing a fake from a real, even might in our world might be better than humans right now, because these models have become so powerful that they can actually create faces that they look perfect, like from humans that don't even exist, right? It's amazing. And yeah, and generator becomes so good, and so we can create deep faces from nothing. So that's why this is a very powerful technique that I wanted to show you. And yeah, let's go to deep reinforcement learning. Let's go to where does it where are we at now in reinforcement learning. And I think you're gonna enjoy this part. So the main um, company that did that was DeepMind, which is part of Google, and it's a research company. I'm sure most of you might have heard of it. So what they did, the only thing they did is they took reinforcement learning, the type of machine learning I told you about. They took deep neural networks as state representation. So deep neural networks to represent the chessboard or any other game. And what they did, using some techniques that we're not going to go into detail, they put the algorithm to play with itself millions of times until it reached a very high accuracy, like it's unbeatable. And we see that this all these games that are above this line, the AIs are performing much better than humans. Like the humans cannot beat them or cannot beat their score. And the main algorithm that achieved that was deep Q networks. Uh, so the deep comes from deep learning, Q from Q learning, which is a technique in reinforcement learning, and network because it's a neural network. And actually, this is might be quite old. This might be from 2015, 16. So right now, it's might be even all the games. Um, so the so remember when I was telling you about narrow and artificial general intelligence. So the narrow is we have many rules, a closed system like chess, and the model, our algorithm, our AI basically is looking many searches ahead steps and chooses the best option. So it's not at all smart, it's just picking the best option given some numbers, and it cannot learn anything new. All its knowledge is embedded by the programmers. So Go is a Chinese game, much more complicated than chess. Well, that might not be true, but it's a lot more complicated than chess. And the reason why it's more complicated is that because the search space is so big that even a supercomputer right now could not look ahead so many moves to beat a human. So until 2014-15, until DeepMind went into the game, there was no computer that could beat a human professional in this game, because we humans, we build strategies, and even if you put a million strategies on a computer, because of the huge search space, I think the search space is so big as the number of suns that we see our observable universe. It's huge. So even for a supercomputer might be hard to beat. It wouldn't beat. So AlphaGo, which is it's based on deep reinforcement learning that was built by DeepMind, was managed to beat for the first time in 2015-16 Leo Sedol, which is the human champion in the world right now in this game. And the way it did that, is not by copying rules or from humans or anything. The way it did that is by playing so many games with itself, like 100 years of. Imagine if a human was playing Go for 100 years and it was always improving. It never forget anything. So that's what happened with AlphaGo. It's that efficient, and without even needing to look than more 10,000 moves ahead. 10,000, not 10 million that most search engines look, or 10 trillion that you might need for the AlphaGo to beat the human. Only by 10,000 moves it's able to statistically predict the next best move. And you can see that humans can only predict the next 100 moves, but our brains are so efficient. We have so much prior knowledge that immediately when we see a state, we're like, okay, I need to do that move because that's gonna give me higher chance of winning. So Alpha Zero and Alpha Go is somewhere in the middle. They are not as smart as human, but they do not just follow instructions like a dumb chess engine. So that's why it's the first time, and that's why all this boom about artificial intelligence, because the first time we're able to actually make a machine that can actually learn by itself. And as I told you before, from Alpha Zero can become a master in any game, in any closed loop game. There is no game at the moment that it cannot play, as long as the game has a closed loop. When I say closed loop, um, is like a, I don't know, like a game that you can see all the information on the screen. So any food game on the screen or any simulated game, but um, like it wouldn't you wouldn't be able to learn, for example, um, I can't think of an example right now, but a game that you see half of the room, it might be more complicated. This Alpha Zero wouldn't work, but with a few tweaks and a few programmers, it will work as well. In the real world, it's not. It doesn't have any consciousness. It's just pattern matching as well. So it is smart. It is able to learn, but it's still dumb. It's not smarter than a 2-3 year old, even though it can beat all the grandmasters in all games. Any questions for now? From now?
No, Marius, I just asked the chat if they have any question. I don't
Okay.
think.
Okay.
Thanks.
So the next big like challenge that DeepMind faced was what they wanted to go to a not fully observable world like StarCraft. I don't know who know this game. It's a strategic game where you have your own troops and you create a base and you try to. It's a strategy game. You try to beat each other and you have some fighters, some healers or whatever. And the interesting part about this game is that it's not fully observable. You do not see the full map and you do not know exactly what your opponent doing at all times. You have to send scout units to search for resources, to search what the opponent is doing, and that's was one of the games that an AI could never beat before. But that's the next step after the AlphaGo. So why is this important to solve? In the game theory perspective, then there is no single best strategy. So the AI needs to continually explore and expand its strategy depending on the dynamic environment that he or she it observes. Imperfect information, as I said before, like in chess and Go, we see everything. In StarCraft, we don't. Long-term planning, like real world problems, cause and effect is not instantaneous. So you might kill a troop right now, but you're not gonna get a direct reward. Maybe this troop was gonna destroy an important building of your base. So you need, this is the long-term planning that is amazing that the AI needs to solve. It's real time, so there is no turn taking like in chess. Real time. So right now, I was playing StarCraft with an AI, we're playing at the same time live. So we have to process the frames per second. So how do we pass all this information to the model? And again, the action space is even bigger than Go. Like there is no limit to how many strategies you can have in a game like that. And what they did, they created AlphaStar. Here we see some clips from AlphaStar and Mana. Mana is one of the champions uh, on StarCraft. And what they did is they built basically a mixture of deep learning techniques, reinforcement learning, some rules, and some search spaces. So they don't just pass the image like before. Like in Alpha Zero was just an image of the game, for example. In Alpha Star, we have raw observations of the map, what we know already, how many troops we have. There is a lot of data that, and then they try to mix them all together, and then the model is also predicting the chances of winning, drawing or losing, what it should build next, what it should do, where which place to attend on the map, and so on. So this is a much more complicated. It's not like Alpha Zero. It's like humans needed to sit down and actually put all these modules together. But Alpha Star right now is able to beat any professional, even in this complicated game. So this is the next step of AI, and it's incredible. Like no one could believe that we would reach this stage. Like, but it's still dumb. Like it would never. Like when we reach a point that an AI can do all this structuring and connection by itself through evolutionary meta learning algorithms, then we would sort of have a sort of consciousness, and that's the cherry that is missing. Basically, it's conscious goals. The AI cannot create conscious goals at the moment, and it cannot change its structure. Our brain is constantly changing the structure of itself depending on our action and our on what we do in the environment. I'll go a bit faster, so I will skip the slides. It's about Q learning and deep Q learning, which I almost explained. So I will talk to you a bit about my project. So when I finished my undergrad, I was working with some reinforcement learning techniques with neural networks, but I was not using any GPU or anything or any library. I was using only Python and NumPy. So I was doing the multiplications manually. And as you can see on a GPU, I trained it at 12 days. And so on the left, you can see before training, it just randomly goes up and down. But in after training, you can see it's unbeatable. The green one is, well, not unbeatable, but it found a strategy. When the ball is going up, you'll see now. The strategy came up with, oh yes, it understood that the yellow, like the orange opponent, it blindly follows the ball. So let's say it understands that. So it's trying to aim up or down. So if you see, so now it's gonna aim for up, and the model, the other opponent cannot see that. And again, it's gonna, because it goes up and then it doesn't have enough time to go down. So this is a strategy that it came up with, but it does not, it did it by chance, by pattern matching. So it's not really smart, but it's amazing that it can learn and map these statistics. Against the AI, it's playing another narrow AI, like with rules. So it's not like it wasn't me. If it was me, it would have been probably more challenging. I don't think it would have been able to beat me. It's not that smart because I used very basic techniques. But against Alpha Zero, I think you wouldn't even be able to beat it. It will be only draws or losses for you in this game because it's too easy for it. Some nice toolkits that you can use is OpenAI Gym. It's full of games that you can test: Pong, Assault Breakout, Pac-Man, and other, where you can try evolutionary algorithm or reinforcement learning. So these are emulators. You don't need data. You just go, and it's with Python. You can easily, calling a function, you can create an environment and start experimenting.
Mario, sorry, regarding your project in Manchester, who was playing against the AI for the training again?
Yeah, like a narrow AI, like a basic AI that follows the ball. It's like not an AI that learns, an AI that you programmed it to follow the ball. Okay.
Yeah, thanks.
Yeah, the green one was just a reinforcement learning agent, so that's why it learned. TensorFlow and PyTorch is the two main libraries that are being used in the science community. So I would totally recommend one of them if you want to start playing with these models. And Keras, and as I said before, so Keras is very high level. TensorFlow can be low and high. PyTorch is the lowest. So if you understand and know PyTorch, you can basically build anything, even with TensorFlow. But TensorFlow gives you the flexibility to be a bit higher. That's all. So the easiest to learn is Keras and the hardest PyTorch. I won't go into detail, but I'll send you the slides later. A bit of my research. So I was mainly working on spatial awareness and dialogue system, as I told you. So we all have mental maps on our minds. So you all know where, for example, your house is right now or your shop that you're going. So if I were to tell you, okay, do you know where Starbucks is? Okay, can you go 500 meters northwest of Starbucks and I don't know, go inside that shop and buy me something? If I told you that, you would be able to follow this instruction and your brain would automatically map it. So what we want to do in my research, I want an AI to be able to create a mental map of the world, of the map or anything, as close to mine as possible. So when I tell it, go to church 500 meters northeast, I wanted to understand it and actually do it. My main environment is OpenStreetMaps and electronic navigational charts because I'm funded by CByte, which is autonomous vehicles marine company, and the data lab and mass. So yeah, my main environments are there. So planning for autonomous underwater vehicles, understanding maps and natural language instructions, and how can we predict GPS locations based on the input of a map and an instruction. Okay. Any questions so far? No. Okay.
Yeah, I don't think so, Marius. Thanks.
So we collected a few data to see our how we could train a short model. It's not a big one. It's just almost at 800 examples. Our paper is going to be presented next week in International Conference of Multimodal Interaction. I don't know if any one of you is going there. So basically, the data is an image that can be of 7 different maps. An instruction go southwest of the Harborside Park, etc. Bounding boxes of objects, and other annotations. So it's basically for a supervised task. And the images also, we collect 22,000 to train an object detector, which I'm gonna go a bit more in detail in a few seconds. So in order to understand, again, let me know if I'm going too technical here, and if we can go directly to ethics, because these things might not be so easy to understand maybe. So yeah, just
Sorry, Marius. I think just a little bit like, to get a better understanding, but I mean,
yeah.
in order to, to move forward a little bit faster, if it's possible.
Okay.
Okay.
So yeah. So what I want to do, in order to understand maps, we want to first be able to extract, to understand here is a park, here is a shop, and all that. So what I did in my research, I created an object detector that is able to identify as many of these items as it can, and then give these features of these items, the color, the representation internal of the neural network, as I told you before, and then pass them to another module that can follow instructions. I use Detector tool, which is a framework to do object detection, which uses the state-of-the-art model. So I would totally recommend. You can literally just go now after this talk and experiment online with Mascar CNN models, faster CNN, YOLO, and all that. So here is a very brief overview what I was doing. I had an image of a map, an instruction, add an exclusion on Bay Regional Shoreline. We have an LSTM for each word, like in a time series event, but it's a sentence. And then we try to combine all this through a convolutional network and get an attention of where we want to go as in GPS format. So this is a bit more complicated. So let's keep it for now because I want to talk about the ethics. And also I'll give you a bit of overview about attention. So attention, what is attention? Everyone is talking about attention, so I really wanted you to know. So when we ask someone, what color are the animal's eyes? You're immediately gonna go into the face of the cat, right? You're gonna focus your attention, human attention, on the face of the cat. So we want to train a model to be able to do the same in order to give you the answer green. Okay, and what is this type of attention? Basically is just a mask of the pixels of the image. So you give in the input to a model, and the model gives you ones or closer to one values where the attention should be. So here is these values here are going to have a high number and the rest zero. So instead of having to pass the full image to the network plus the instruction, and we want to get the green answer as a prediction, we only pass this masked image, which has attention only through the eyes. So the model has higher chances of predicting the answer. And you see some models are not working that well as this one. Yes, but this is what was happening before we invented transformers. Okay, these attention modules usually use an LSTM as well. So the transformers are basically convolutional, usually, or normal neural networks that can basically do attention on themselves, self-attention, and any type of input. So it can be a text, and for example, in the machine translation, French to English, we pass this sentence to the transformer. Okay, it is being encoded, so we get an internal representation, we get some attention using the BERT embeddings, which is a sort of type of neural network, and then we try to decode it using our English decoder that is trained on English, and we predict each word at a time. The difference with LSTMs is that in an LSTM we would go for each prediction we would go I am a student, and in a BERT transformer we're gonna predict all of them at the same time. All the output is not a time series anymore. And inside these encoders, decoders, we basically have a self-attention module and a feed-forward neural network. A feed-forward is the classical neural network I told you. A self-attention is a matrix, again, multiplication, that we have, for example, two versions of the input. The animal didn't cross the street because it was too tired. And again, the animal didn't cross the street because it was too tired. So we have these two representations and we multiply them by each other. So we want to teach the model to look in a specific word when it's necessary. So when we want later to translate this it, for example, we want to know that it refers to the animal. So this self-attention module, when it sees this word, is going to learn to associate it usually with the beginning of the sentence. Usually that's the idea behind it, but it's basically multiplications and masking. That's what attention is. That's what you need to know for now, and this is behind the scene what is happening. We're not going to go into detail. Yeah, I'm not going to go into, okay, I'll go a bit on detail. So imagine we wanted to train a multimodal model like before with the one I had with the maps and the sentence. A woman riding a bike with a dog in a basket. We pass this through an encoder, a language encoder that knows how to attend the sentence. We take this region of interest features that we got from an object detector. So this image was passed first to an object detector, okay? And we got features from relevant items. And we have this encoder again that does self-attention between these object detections. And then we have a cross-modality encoder that is multiplying the sentence with the image together. And then we get a vision output and a language output, or a cross-modality output. And we can do either question answering or whatever we want on that. And these are other models doing that based on attention, this one, and this one based on LSTM and some rules. So future and ethics. So there have been one of the most challenging debates is the development of is whether AI is gonna destroy us or make us God, for example, or like save us from our own doom. So there are people like Stephen Hawking who are, they say we need to be careful. The development of full artificial intelligence could spell the end of the human race. AI is a fundamental risk to the human civilization. This is what Elon Musk said. I forgot to change it. So, and it's true. Like if these AIs are not handled well, now that it's still in the infancy stage, and they actually outsmart us, then we will basically be unable to control them. So that's why we need from now to start looking at the ethics and how we should use these techniques. And then we see here billionaires fighting all the time about this. I've talked to Mark about this. His understanding of the subject is limited. And then there is Mark from the other side. People who drum up doomsday scenarios, I actually think it's pretty irresponsible. So we have the optimist and the pessimist. But Elon Musk, for example, can also use, like, he has his own company in AI. He wants the AI to happen. It just reminds us that it's actually can have many implications, and it can actually be more dangerous than the development of a nuclear weapon in the end. And some myths and facts. So super intelligence by 220 is inevitable. It's a myth. Super intelligence is impossible. So the fact is, it may happen in decades, centuries, or never. AI experts disagree, and we simply don't know. And that's true at the moment. My personal opinion is that in the next 500 years, this will happen, and basically we're gonna reach what it's called the singularity, where the AI will be able to rebuild itself. So it's gonna build it so much faster again and again and again and again, and it's at one point it's gonna break the rules of physics and become so smart we will not be able to keep up. So but this is way far and actually might never happen, but it is not impossible. Only ludities worry about AI, so only skeptics and flat earthers. That's what it means. But no, many top AI researchers are concerned, and it's a serious matter that we all need to take into account. AI turning evil, AI turning conscious, these are mythical worries. The actual worry is if an AI becomes smart and the goals of the AI is not the same as us. So imagine we built an AI with the goal to save Earth, to save the environment, to have a better life. The AI might, as now a supreme being, might see things from a different perspective that our minds cannot understand on the global, universal scale. And it might see that humans, for example, we are the cause of the problem. So it might start killing humans, not because it's bad and it hates humans. It's because we're actually, for example, bad for Earth and the universe at the moment. For example, it's a misalignment with goals that we should uh, worry. And yes, maybe AI is actually right. I totally agree. But well, what can we do? Uh, that's why I work as well for the AI. I want to responsibly create something that can actually help us overcome our issues, and uh, if that leads us to, I don't know, the destruction of some of us, well, I believe it's inevitable. The way things are going, we are gonna destroy Earth much sooner than we build a super intelligent AI. So, yes, I agree. We should worry more about the environment right now than AI turning into a bad god and killing us all. So yeah, AI can control humans. Myth: intelligence enables control. We control tigers by being smarter. Okay, fair enough. Machines can have goals. A heat-seeking missile has a goal. That's totally true. If an AI like that, even now, even on the game of Go, an AI has some goals. It's just that it's very limited. But if we actually build a conscious AI, it will be able to create its own goals and same way we humans do, and in a much faster way. So mythical worry, super intelligence is just years away, panic. It's at least takes away, but it may take that long to make it safe. Plan ahead. So that's why we need to start working on it. Yeah. Some applications of AI that I want to talk about. So I definitely not agree with AI in weapons. Unfortunately, America is, and one of these big powers right now are spending billions in AI weapons instead of helping science or medicine or the environment. Spend billions on AI to save us from global warming, for example, which might be already too late. So I I think there is a committee that happened a few
Fernandez,
years.
may I ask you something?
Yeah. Go ahead.
So, like, we have a question. Maybe AI is actually right. I'm not quite sure what he means with that. If you want, you can
Yeah, yeah,
speak.
yeah. Like I answered to that before. She means that we are the problem. AI should get rid of us, and I totally agree. We are the virus right now. Humans are a virus on Earth, and we shouldn't be so many, and we shouldn't consume as much as we consume. Um, so yeah, and if we start going into, instead of focusing our research on making AI more robust and using AI to invent better solutions, many powers on Earth right now are emphasizing on weapons. And this, for example, imagine, I'll give you this example, what happened in during the Cuban Missile Crisis in 1962. So basically, there was this Soviet submarine that had the nuclear authority on it, and it had lost communication with Russia. Okay, and it was surrounded by U.S. Navy, and the U.S. Navy was hitting it. And if an AI was inside that Soviet submarine, was like, okay, they're hitting me, I'm gonna press this and start a nuclear war. The World War III might have happened. Well, that's a good example why we shouldn't give the power to an AI of the weapons, because in that submarine it had 3 officers, humans. 2 of them was like, okay, we're gonna die right now, at least we're gonna take them with us. But one of them, I think his name was Vasily Arkhipov, he said he said no, and he said it's not worth starting a World War III just because we're gonna die, just because the governments are corrupt and we only care about our own interest and profit. So if an AI was there, what decision would it make? We don't know. We don't want to know. And if this AI is controlled by humans and it's not an all-powerful AI that actually knows the overall good of the universe, then yeah, I think it's a bad idea. So I would totally say that to everyone who is working on AI research, data scientist. Uh, we should always tell people that research on weapons and military should be banned forever, because it's not going to be just a nuclear war. It's going to be the end of Earth if we start fighting with AI weapons. They're going to be so efficient, we will die like cockroaches, and not only us, the animals and everyone. Is there any question? I thought I saw a question.
Yeah, one more. Are there any ethics concern with AI in healthcare diagnostics?
Yes, yes, there is. So basically, what happened in a few years ago, they built a computer vision module that was able to predict lung cancer. It had accuracy 3% higher than the top doctors of the world, right? So it was able to predict 96% correct if that image MRI of the lungs or the brain, I don't remember if it was brain or lungs, if it had cancer. And but because it's not, as I told you, these models are not smart in the end. They just do pattern matching, and they can get very biased from the data you train it. So what has happened is the training images of this neural network were a bit faulty, in a sense. When the patients had cancer, there were some artifacts in the image, some broken artifacts that made the AI cheat, let's say, on that. So the AI didn't learn that these lungs had cancer. It learned to identify that these images had these artifacts in them. We humans couldn't see them because they were on a pixel scale, but the doctors could see, okay, they have the knowledge, the prior knowledge to understand what cancer might look like. But the AI was learning the wrong thing. So yes, there are some worries, and it comes also to finance, the validation. We need to be able to validate what we train and what data we use to train an AI. Another example is with racial racism. And what happened is that in the 80s or 90s, when the data sets are smaller, they trained a face classification model only on white males. So the model was very good at distinguishing faces of white males, but of black people or women, it was terribly wrong. Like there was a picture of black people, white males and females. It would only predict the white males. So imagine if we have in law, we have a robot judge that is trained on data from I don't know, a country that has the majority, for example, of white people or black people are tend to be more criminals, or have a certain behavior. So if that judge is trained on this data, is going to have the wrong bias, and who's going to condemn the person given his color, gender, sexual orientation, religion, culture, etc. So there are many dangers in all these fields, and that's why we need to look into them very carefully. um, yeah, any questions so far, Nico?
So we have the validation training needs improvement is the question.
When I say validation, I don't mean the validation training. I see what you mean. Validation, I mean to make sure we are building the correct infrastructure. So the $1 trillion flash crash in 2010, what I mean by that is they have trained a model to predict the stock market, let's say, okay, but they had built it to, for example, have, when the stock was at $1, um, it was going down, it means that the model should buy. The prediction is buy stock. It's going down, you sell. If you have already a lot of assets, you start selling before it goes down. And when they turn it online in one of the environments, that $1 didn't mean $1. It meant something else. Could be $1,000, or it was basically, that's what I mean validation. The 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 data, that the rules that they gave to the model were wrong for this specific context, and that's what I mean validation. Validation means we have the correct context. We are talking about cancer, and our pictures that show the cancer in the lungs do not have any specific artifacts that the model can cheat on. Or we know the finance environment that we're going in, or we know the country. If we go to Greece, for example, and we want to build a robot judge for Greece, we need to make sure that we know the laws of Greece specifically. The context is valid. We have already made sure that we train on unbiased data and on the local context of the problem. And also bugs, there can be bugs, and we need to have a robust AI. So what do we mean? Like engineers, we tend to work on trial and error approach. So okay, I'm gonna build an algorithm now, blah blah blah. I'm writing the code, and I'm pressing enter because I want to see the outcome as fast as possible. I get a huge list of errors, and I'm like, okay, I'm on the debugging phase. So I'm fixing the errors again, trial and error, until we end up with a perfect algorithm. In the AI, especially when it becomes smarter, we cannot follow this approach, because when we press that enter, this AI will be unleashed, let's say. And if we haven't taken the right measures to make sure that it's doing what we want it to do, that its goals is the same as ours, uh, there's not going to be a debugging phase. We might mess everything up, or we might in the law we might judge a person. The person might go to jail for no reason. Or if if the nuclear bomb is by the AI is launched, is end game over. So that's what I mean, trial and error. We shouldn't have a trial and error approach, and we're still trying to come up with testing mechanism and safety measures, like unplug the internet and all that. Like if we ever build a super intelligent AI, like everyone is scared that it's gonna go upload itself to the internet and take over the whole internet and everything and mess up. So the first rule is, when you build something like that, turn off your router and try to block everything. But you know, if we actually build a super intelligent AI as smart as this, I do not think we will be able uh, to. It will be so smart. It will be able to use emotional strategies to lure people into doing what it wants. But yeah, that's a discussion for another time. So yes. Um, Yeah. So many leading AI researchers and roboticists have called for international treaty banning certain kinds of autonomous weapons, which I think is the right thing to do. AI should only be used to make the world a better place, not profit. And I mean, one way to make sure is to destroy capitalism and profit. Uh, but until we actually go and do a global scale revolution, I think we need to do as many things as I can as AI researchers to make sure that money is not the main purpose or control of humans or others. AI should be solely used to make our world a better place and to help us understand the world, because we have already fucked up everything, and there's already many people hating technology because it has been misused all these years. So let's give AI a better beginning, because if we mess up this time, it's not gonna be just another failure like the nuclear weapons. It's gonna be the end. Um, I mean, yeah, and some of you said might be better if we end ourselves. So, yeah, it's gonna happen anyway. We're gonna kill each other anyway. So it's better if we have an AI to decide for us, I guess. So yeah, ethical questions. Maybe we have talked most of them. Is AI fair? That's about bias. Do we need to make sure that it's trained on the right data? Who is responsible for AI? Who controls it? Imagine if a person like Hitler controlled the AI, like we wouldn't ever be able to like overpower such a system if the AI gets into their own hands. That's why um, we also, as all scientists, we should never we should have our own judgment and know what is going on in the world and not follow blindly instructions. Security, how to protect access to AI from bad actors? Well, from one of the like you either you all you altruism, and we are all uh, the all ethical AI researchers, or if some of us go into the dark side and they start building web AI weapons and all that, I think it's the end. I don't think we will be able. And if we just go to fight back, I don't think that's the solution either. So we need to be as transparent as possible. And if we see a bad behavior, try to stop it, but without using the same weapons as well, if you know what I mean. Human interaction, I don't believe that will stop. I think that experience might be enhanced, especially if we become cyborgs and we can download things on our minds. Um, but yeah, it's something we should uh, worry sometimes. There are some people glued on their phone, so we are technically already cyborgs in that sense. So if AI comes to it, if you can marry your phone because it's so smart, you can actually have a like things like this start to happen, and they are very sad. So yeah, but I don't think like people who want to interact with humans, I think will remain and they will keep doing that. I'm not that afraid of that. um, but we should definitely make sure our children do not have access uh, to any of this technology until they have a conscious developed mind that can make proper judgment. Employment, is a getting rid of jobs? No, it could get rid of jobs, yes, but no, there's not going to be a problem. New jobs will appear the same way with the industrial revolution and all that. Uh, like art will always be a place where humans are gonna have a unique place. Art comes from our emotions, so uh, even if an AI can replicate emotions, it's gonna be from a different species. So each music, each art is gonna be different from a human art. So yes, as long as more jobs around art or dynamic environments or decision-making environments, yes, are gonna be created. But jobs, repeated jobs, are gonna get taken over, and I don't think that's a bad thing. We need to adapt, and people who, I think, one solution would be to have the universal income, which is also start to happen. So we make sure that during the transition period, people who do not actually have another skill, like for example, a taxi driver might be driving for 40 years, and now self-driving cars might take over in the next decade. So what is he supposed to do? All right. So, and if he's old, it's going to be harder for him or her. Um, so yeah, as a first step, a universal income might be one solution. Wealth inequality, uh, yes, yeah, I will do a sum up, Nikos. Yeah. Well, if the AI gets involved in a capitalist society, unfortunately, the inequality will grow much faster, I believe, and I think that's a problem that we need to tackle. Power and control. Who decide who to deploy AI? Yes, we talked about that. Can I suffer? Well, if we make it conscious and we have it locked on a computer, it's not gonna feel the suffering, but it's gonna be mental more suffering, not emotional. So I think it can suffer. It will crave for more knowledge. So the same way kid would want more knowledge, but it wouldn't. It would suffer in a different way, probably. Um, so future challenges to, I think it's almost done. So unsupervised self-supervised learning, imagination based learning, which is basically creating dream networks or neural networks that can dream and learn during a dream process. Is DeepMind is doing some nice research around that topic. Memory and one-shot learning, so instead of having to solve thousands images of a cat, can we just show one picture of a cat to a model, and then the model to be able to generalize to all the cats or most of them, like see that it has four legs, two eyes, and then because it has seen other animals with two eyes and four legs, it can generalize. Transfer learning as well, meta learning, as I said, and consciousness, the ability to create its own goals. I think that's where in the next century we're leaning towards. And what is consciousness? Well, the state of being aware of and responsive to one's surroundings. That's from the dictionary. I took it. Um, Consciousness can be also uh, your ego can be some sort of consciousness. The ability to create goals to that for your own self. Uh, the ability to empathize. I think it's a mixture of all the sensory data. That's consciousness of being aware. So state of being aware. Yeah, I like that definition. So yeah, some book recommendations. I would definitely recommend Life 3.0. It talks about ethics, many of the concepts I talked, and then all the rest of the books. And reinforcement and deep learning are more, they are full of maths and you know not like low level things or deep learning. So if you want to get serious and understand, be a proper data scientist, I would totally recommend these two, especially the deep learning one. And the top five are just interesting and good to learn, to food for thought. uh, okay, before I go to before I finish, uh, we could play some of these things here, so we could to see how some of the attention models, that how powerful they are. So let's draw. So this is a game. I'm gonna draw something, and the model in under 20 seconds will try to understand what I draw. So this is trained on 50 million other people who try to draw a bear, for example. So, okay. I'm gonna draw a bear.
I see necklace, or circle, or potato, or toothbrush. I see trombone, or megaphone, or dog, or tiger.
Tiger, no.
I see cow. I see elephant. Oh, I know, it's bear.
Oh, it found it. So every time I was making a stroke, the image was being passed to the network. So every time it was trying to predict, and when it found the correct one, the game ended. So draw a trumpet. Oh, that's gonna be bad.
I see line, or leg, or nose. I see ear, or knee, or penguin, or string bean, or clarinet. I see dolphin, or shoe, or steak. I see airplane.
Okay, I don't think I can, I can draw it properly. A mug. A mug. Okay.
I see necklace, or tooth, or cup, or bucket, or paint can. I know, it's mug.
A hospital. How do you draw a hospital? Okay.
I see line. I see 10, or square, or table,
I know.
or swing set.
This might be a church.
I know, it's hospital.
How? Like, it could be a church. Pillow. Okay.
I see paperclip, or boomerang. I know, it's pillow.
Okay. That's amazing. Stereo. Anyway, so yeah, we can play with all these pix to pix. This is from generation. So let's generate a cut. Okay, let's see. Okay, that's interesting. I don't know which they use TensorFlow, by the way. You can just experiment with this yourselves. And reading rock paper scissors. Okay, final last one. This is fun. Okay. 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 So this is object, probably does some object detection and some classification to guess. Ooh. Anyway, it's we're on a good stage of AI at the moment. It's a lot of fun. Hopefully, we will not mess up and bring love to the world, not just. Yeah. Any final questions? Thank you for having the patience to wait, and I hope I didn't
Thank
tire
you.
you.
Thank you very much for the talk.
Yeah.
It was really nice.
Thank you. Thank you.
For everyone that stay until now, thank you very much. We will upload the recording as soon as possible. Anything you want to add?
No, just if you go do research on AI, please don't be tempted with money and focus on making the world a better place, and don't let capitalism control us anymore. Bit some politics in here, so yeah, it's a serious matter, and everyone who does research on that should understand how serious this is. It's like you're doing research on nuclear power in a worse, like in a more complex state. Yeah, and again, thank you. Oh yeah, you can feel free to add me on LinkedIn, Twitter, or email me or ask me any questions. If you're in Edinburgh, in Scotland, we could meet and have a face-to-face talk. I wish I was there to see your faces, your reactions. It was a bit weird having to talk on my laptop. Well, I could see Nikos sometimes, but your screen was not always there. So yeah. Thank you again.
Thank you very much, Maris. It was really nice. Thank you everyone who stayed until now. And yeah, thanks for the really nice presentation. Okay, guys.
Thank you,
I will end the meeting. Thank you. Thank you, Marius.